Good morning to all. Imagine this. If you want to travel from Florence to Pisa, which route would you choose? Of course, it depends on the situation. If you travel early in the morning without traffic, you may select a particular route. The same route you may not select if it is heavy traffic. You might select a completely different route if in case of heavy rain. This means that every time you select a different path. However, when you select the path, the selection depends on two parameters. Which are they? Number one, you need to reach your destination as soon as possible. That is shortest distance. Number two, make sure the route is safe while traveling. That is secure path. Why I'm talking about this example now? Because this example is really connected to the theme of my presentation. The theme of my presentation is network security through route shuffling. In the network, if we want to send a packet from source to destination, then we need to select a path, and the selected path should be secure and shortest. How it is possible? To get that answer here, I would like to briefly explain about my research work. A very warm welcome all of you for my presentation. I'm really thankful to Professor Tomasa and Professor Romano for giving a wonderful support during my research work. An American motivational speaker, Mr. Lee Brown, once he said a profound statement, that is, your goals are the roadmaps that guide you and show you what is possible for your life. I would like to borrow that statement here. I would like to show you what was possible for me when it comes to my research work, what research I have done. The goal of my research was to apply graph theory in the computer network for routing. How can we make sure that our routing is effective? When selecting the route, the selected route must be secure, complex, and shortest distance. Theoretically, it is possible by applying the concept of graph theory. As you can see in the slide, the goal of my research is very simple. However, the actual implementation is not that simple. To achieve this goal, we have done research on various algorithms and the concept of a graph theory. Now, let me talk about the concept of graph theory that we have used in this work. The first one is spanning tree algorithm, and the second one is shortest distance algorithms. For spanning tree algorithm, we focus on secure and complex network, whereas in the shortest distance algorithm, we focus on shortest distance between source and destination. Well, as a spanning tree algorithm, we use backtracking, primes, and counting algorithm. Well, in the case of shortest distance algorithm, we used Dijkstra's algorithm, improved version of Dijkstra's algorithm, and then finally, edge swapping and fitting algorithm. Perhaps you might be wondering, backtracking, primes, Dijkstra, all these algorithms are established. Then what additional work or research we have done during the development? Let's see the next slide. That is our contribution. As you can see on the right side of the slide, algorithms are implemented in different programming language. For example, backtracking, primes, and counting, all these algorithms are implemented in C language. And then finally, we have combined all these algorithms with the help of C. Then with Python language, by calling all C programs, we have generated all the minimum spanning tree from a given graph. This is one of the findings of our research work. We have generated minimum spanning trees for 20 network graphs. When it comes to shortest distance algorithm, of course, Dijkstra's algorithm is already established. However, we have implemented improved version of Dijkstra's algorithm. Then with the help of edge swapping fitting algorithm, we have generated the best fitting for the network graph. The combination of edge swapping and improved version of Dijkstra's algorithm is a completely new concept in graph theory, and the implementation is done in Java and Python. And nowadays, number of algorithms are used for routing. One example is vector-based algorithm, but here we use spanning tree-based algorithm. What is the reason? At least three reasons I would like to mention here. The first one is the number of spanning tree of a graph increases exponentially with the graph size. And the another reason, the features of spanning tree, that is, if one of the nodes fails in the network, it disconnects a bridge, then it rebuilds the network, then the network continues to function. Then finally, using spanning tree algorithms, we can have a maximum variation. These features are very useful for complex and secure network routing. By this now, I spoke about the basic concept that we have used in our work. Now, let's talk about the actual thesis work. First, we have used one of the fastest algorithm called backtracking to find all the spanning tree of a given graph. For this, we have used a depth first search technique. Then we realized that all spanning trees are unsuitable for routing. Only minimum spanning tree are used effective for routing. So our next goal was to find all the minimum spanning trees. To obtain minimum spanning tree, we use Prim's algorithm. But there is a problem. In the network graph, there will be number of minimum spanning tree. But Prim's algorithm will not tell you how many minimum spanning trees are available for a network graph. So what we have done, we have applied Cayley's formula in Prim's algorithm and generated the total count of minimum spanning trees. Now we got the total count of minimum spanning trees. So the next step is to print those minimum spanning trees. For this, we have used Python program. Then finally, with the help of generated minimum spanning tree, we have sorted minimum spanning tree in increasing and decreasing order for effective routing. Now we will see the experimental results of our research work. On the right side of the slide, you can see that we have tested nearly 20 network graphs. The number of nodes for these network graphs are same, that is 10, but the number of edges are different. In the second column, you can see the results of the total number of spanning trees. Of course, the total number of spanning trees large for each network graphs. But in the third column, you can see the total count of minimum spanning trees. And we are more interested in third column because minimum spanning trees are good for effective routing. Then next, we have selected some random graphs with a different number of nodes and different numbers of edge for testing. As you can see in the graph P1 to P7, as you can see from the table, the total number of minimum spanning tree increases as the number of edges and nodes increases. Based on this experimental result, I would like to mention some concluding comments on our findings. After generating all minimum spanning tree with the help of Python program, we realized that if we sort these minimum spanning tree in increasing and decreasing order, then we can make a complex and secure network routing. And another point is that the total number of minimum spanning tree depends on various factors like cost of edge, number of nodes, number of cycles in the network graph. Then finally, we learned that when it comes to shortest distance, minimum spanning tree algorithms are not useful because in minimum spanning tree, the requirement is to reach each node once and the total cost reaching each node is required to be minimum among all possible combinations. But that doesn't mean that from each source to destination we have minimum distance. But sometimes for effective routing, we need shortest distance between each source and destination. For this, we have done research on some other algorithms. Which algorithms? Let's see in the next slide. That is shortest distance algorithms. The basic concept of these algorithms is to find shortest path between nodes in the graph. So now let's talk about more on these algorithms. Here, I don't want to explain more about Dijkstra's algorithm as it is already established, but why it is needed an improved version of Dijkstra's algorithm. For example, in the graph, if there are more than one vertex having same priority, then the problem with existing Dijkstra's algorithm is that the minimum that we are branching might be selected by the other ones as next cycle. So in this case, we will have duplicates of trees. So we need to avoid that duplication. That is the reason we implemented improved version. How did we implement it? We'll see in the next slide. On top, you can see that we have implemented Dijkstra's algorithm with the priority queue in Java. Then for an improved version, we have added additional 4 steps in existing Dijkstra's algorithm to avoid duplication. The first step is we create a check property for finding if in case more than one word is having same priority. If no, it goes as normal Dijkstra's algorithm. But if yes, then we go to step number 2, that is duplicate intermediate results, dist and prim. Then the step 3 is store the list of candidates and predecessors. Then final step is from the list of nodes and predecessors, we generate graph without duplication. Please note that all the test results are based on improved version of Dijkstra's algorithm. Here we can see the experimental results of improved version of Dijkstra's algorithm. The same 20 network graphs which we have used for testing minimum spanning tree are used here for testing. As you can see here from the test result, at least 2 to 3 alternative variations are possible for each source and destination. But that is not effect for effective routing. We need more number of shortest distance paths for each source and destination. For that, we have applied edge swapping process algorithm. 4 steps of edge swapping algorithms are mentioned in this slide. By applying this algorithm in the network graph, we get more variations in shortest distance. As you can see here, the variations are increased now, and at least 4 to 5 alternative variations are available for each source and destination. So the next step is simple. Just we need to sort generated shortest distance path based on similarities and dissimilarities. And then with the help of Python, we print the best fitting distribution for each network graph. And that we can see in the next slide. The best fitting distribution for graph 23, you can see here in this example, the best fitting line is called gamma. Now, let me provide some concluding comments on shortest distance algorithm. Since we have a number of variations for each source and destination, it is fast and effective algorithm. This algorithm is suitable when we need shortest distance for routing. Since we have more variations for each source and destination, we can make a complex network routing. At the outset of this presentation, I said that if you want to travel from Florence to Pisa, you choose a secure and shortest route. What about complex? Of course, you will not select a complex route. But what about network routing? In network routing, we need a complex structure. How it is possible? It is possible by using variations in paths. How path variations are possible? It is possible by applying graph theory. When we apply graph theory, each cycle we use completely different path for routing. So what will be the result? It will be too complex for the attackers. They will not be able to understand the routing structure, and this is what our goal was. So we suggest when it comes to a huge network, a spanning tree based network routing is one of the solutions to avoid possible attacks. When shortest distance is a primary concern, then we understand that shortest distance are good options than minimum spanning tree for network routing. Thanks to all.